Okay, so to follow up on what we've already been talking about with logarithms, this next section discusses in more detail kind of how logarithms work. So we're going to look at some laws of logarithms and kind of what we can do with those. So let's just get right to the three main laws of logarithms. The first one is called the product rule. The second one is called the quotient rule. So by the way, the names of these rules should seem familiar to you, right? And the third one is the power rule. What kind of rules have we already talked about that have these same names? Exponent rules, right? And remember, logarithms are just fancy exponents anyway, okay? They're just really the inverses of exponents. So here's the product rule as far as logs go. If you have the log with a base and you have m times n, so rather than you multiplying exponents, notice we're taking the log of something being multiplied. That is the same as adding the two individual logs together. So I know we're not as comfortable with this form, but what did we do with the exponents when we did the exponent version of the product rule? Didn't we also add them? Okay, so it's the same rule, just albeit a different form. Okay, so quotient rule is going to be for when you're taking the log of two things being divided by each other. Okay, so what do you guess is going to be the quotient rule version of law of logs? Instead of a plus, we're going to change it to a what? Subtraction. And isn't that exactly the operation we do when we do the exponent rule too? And then last but not least is the power rule. The power rule is actually one of the more useful log rules. And what it says is that if you're taking the log of any base of something with a power, you're allowed to move that power actually to the front of the log. Okay, so essentially we're going to move the p to the front, and then we're still going to take the log base b of m. And just know that these rules work for all bases. So they work for any base at all, including natural log. Because natural log, remember, is just a log with a base of e. So we're going to practice these rules kind of backwards and forwards until we know them really well. And then we're going to use them to maybe solve some scenarios. But before we're ready to do that, we're going to need to make sure we know the rules. So I want you to expand this using the laws of logarithms. Expand means to make it bigger, right? So we're used to simplifying things, and I'm asking you to do the opposite of that in this next problem. So if you have the natural log of x times y, okay, what's the understood base here? The understood base for ln is not 10, but what? It's 10 if it's log log. When it's ln, it's base what? E. Okay. But my only point in that was just as a review, right? So what rule do I need to use here? Like, what operation are you doing between x and y? You're doing product rule, right? So what product rule says is I'm allowed to separate them / expand them using addition. Okay. So this is what product rule looks like. So let's do another one, and I'm going to be lazy. Let's say the same instructions. In other words, expand the following using logarithms, using your rules. So log base 3 of 9xy. So same rule, it's just this is log base 3 instead of the special case base e as before. So what am I going to do with, first of all, how many parts am I going to have? Because I have 9 times x times y. So like how many different log parts am I going to have if I pull them apart? 3 total, right? So I'm going to do the log base 3 of 9 plus the log base 3 of x plus the log base 3 of y. Okay, notice that I don't change the base, right? The base was 3 and the base stays 3. Okay. However, I think this one could be worked out. Anything with a number in it, you need to try to evaluate it if you can. Okay, so what is this really asking, or what is it really saying? This is saying, what do I need to raise 3 to the power of to give me 9? And there's a clear answer there, right? Like, what would I raise 3 to the power of that would give me 9? 2? Okay, so this would just becomes 2 plus the log base 3 of x plus the log base 3 of y. Notice my goal actually was to expand the exponent, and I've done that, right? I've written them all each as their own piece. And again, by the way, this was product rule. So any part that can be evaluated, I want you to go ahead and try to do that. Notice we don't know what x or y is, so there's nothing that we can do with that. All right, but let's practice using some of the other rules. But same instructions, I want you to expand it using one of the 3 rules. You only have 3 to choose from. So what about the log base 5 of x to the 7th? So which of the 3 rules does it look like we would use here? Power rule, right? And what does power rule tell us we're allowed to do with the power? Move it to the front. Okay, so this is essentially the same as 7 times the log base 5 of x. Okay, so all we're doing really here is just practicing the 3 rules. We're not really solving quite yet. We're not really there yet. We've got to learn the rules first. And I don't know why I went from 2 to 4 there, but that's example 3. All right, but let's do another one. So what about the log base 4 of 16x squared over y? So note I actually have 2 rules at play here, right? I'm multiplying 16 times x squared, but then I'm dividing by the y. Okay? So how many different log parts do you think I'm going to have based on what I have inside here? 3 parts, right? So I'm going to start off with the log base 4 of 16. Okay? And then I'm going to add the log base 4 of x squared. Okay, why did I add those 2? Because what was I doing over here? I was multiplying 16 times x squared, right? But then when I switch to the y, now I'm doing what? What operation? I'm not multiplying anymore, I'm what? Dividing. So I've got minus the log base 4 of y. So then we simplify what we can, and we also have one more expanding step we can do. So one thing we can do is this 2 can come to the front of this log. But the other thing that we can think about is what can we do here? Right? Similar to what we did in example 2, what do you notice? Like, how could I think of this differently? 4 to the what gives me 16, okay? And what is the exponent that would give me 16? So remember, we want exponent, not what times what, right? So it's 4 times itself twice, right? So the answer here then is 2 plus this 2 moved to the front, right? So 2 log base 4 of x, and then minus log base 4 of y. So before we look at another one, notice that anything that was on top stays a positive log, and anything that was on bottom is a negative log, right? Because logs are just fancy exponents, okay? And what do negative exponents mean? They mean fractions, right? So that's essentially what you've got. Anything on top will be a positive log slash exponent. Anything on bottom will be a negative log slash exponent. Okay, so we're going to do 2 more. These are kind of the most difficult ones of this little section of problems. So I think if you can do these, you can do any of the ones like this on your homework for sure. You just have to kind of slowly but surely get the problem in a different format using the 3 rules. So we've got the log base 2 of the square root of x divided by 8 and divided by y squared. So before I even start with my rules, I'm going to rewrite this as x to the 1/2 power. And if you didn't know to do that, again, that just might be something that you need to review, your unusual exponents. Remember, roots are fractional exponents. Okay, so how many parts will I have to this log again? I've got 1, 2, 3 distinct pieces, right? So I'm going to have the log base 2 of x to the 1/2. But then I start doing what? I'm dividing, so what do I need to put as far as signs go here? Subtraction, so it's going to be minus log base 2 of 8 and minus log base 2 of y squared. In other words, they both need to be minus because they're both on bottom. Okay. So now I need to maybe use my power rule to bring this to the front of this guy. Power rule can bring this to the front of this guy. And then this can be evaluated. Y'all tell me what it is. What is the log base 2 of 8 and y? It is 3. And how did we get 3? Because it's really saying, what do I need to raise 2 to the power of to give me 8, right? And the answer is 3, okay? So the full expanded format looks like this. 1/2 log base 2 of x, if I move that 1/2 to the front, minus 3, right? Like the whole log base 2 of 8 was 3, okay? And then minus 2 log base 2 of y. So I don't really consider these to be maybe the most satisfying answers in the world, okay? Especially since we're not really simplifying, we're actually doing the opposite of that. But just remember, the point of these problems is for you to practice those 3 rules and know them really, really well. All right, so last one like this. And then we're going to practice using the rules in another way. All right, so let's say you had the natural log of the cube root of x squared y over 8z cubed. So that's kind of the mother of all logarithm rule problems right here. It looks ugly, but I think that we can handle it. Okay, so the first thing we're going to think about is this is essentially just this fraction raised to the 1/3 power. Why is it 1/3 power? Because what kind of root is it? It's cube root, right? So it's 1/3 power. Okay, so notice this 1/3 power is going to go to everything. Okay, so I'm going to say we're going to distribute the 1/3 power to all terms. So this is what we're going to get if we do that. It's going to be the natural log of x to the 2/3 power, because 2 times 1/3 is 2/3. And then it's going to be y to the 1/3 power, because the y gets the 1/3 as well, over 8 to the 1/3 power, and then over z to the 3/3 power. Okay, so notice, what did I do with all 4 parts? All 4 parts got the what power? The 1/3 power. Okay, so I think there's some cleanup that we can do, and we're going to. Okay, so we'll kind of do it as we go. So it's going to be the natural log of x to the 2/3. And then what? What sign goes here, because this one's also on top? That's going to be a plus, right? And it'll be y to the 1/3. But then what do I have to switch to since these are on the bottom? Minus, right? So this will be 8 to the 1/3. And then minus the natural log of z to the 1st. Okay. Notice 3/3 really is just 1, right? So I just went ahead and changed it there. One more thing is I can go ahead and work on this, right? Like, what is 8 to the 1/3 power? It just really means the cube root of 8, right? So how could I rewrite the cube root of 8? So I'm going to kind of mark this out with a dashed line there so you can still see it. This is just the same as 2. And then last but not least, as far as expanding goes, each of these exponents needs to move where? To the front of their piece, right? So the final, again, not super satisfying form is this term in fully expanded form plus the second term minus the natural log of 2, and then finally minus the natural log of z. Okay. Note that you need to make your z's different from your 2's somehow. So I do that by doing a slash mark through my z, but especially if you don't write a big bubbly 2 like this, especially if your 2 looks kind of like this, okay, you need to make sure you differentiate between your 2's and your z's. By the way, I cannot really figure out ln of 2 in my head. How come? Even if I tried, what's ln of 2 really asking? What do I need to raise e to give me 2, right? And that's not a number I can do in my head, so I just leave that alone. Okay, so we did a lot of problems where I asked you to use the 3 rules. Honestly, most of the problems, though, where you actually need to use logarithms will be going the other way, where you start off expanded and you combine to a single logarithm. So we're going to go backwards now, okay? But this is actually probably the more useful of the 2 directions. So what I mean by that is, what if I asked you to simplify this? Okay, so note that we have the same base, right? And note that we have a plus sign. So what rule uses addition? Which of our 3 rules uses addition? Product rule, okay? So if I use product rule, not only am I allowed to take it from condensed form to expand it, I'm also allowed to go from expanded form back to a single logarithm, okay? So this would be the same as the log of 5 times 2. But we can do 5 times 2, right? It's 10. And then I even think we can figure this out, right? Because what's this really asking? So what's the log of 10 really asking us? What's the understood base for log log? 10. So 10 to the what is 10? And the answer is just what? 1. Okay. By the way, notice that you wouldn't really have been able to do these individually, right? You would have asked yourself, what power of 10 gives me 5? And you'd be like, well, I don't know, right? What power of 10 gives me 2? I don't know. But when you combine them together, it's an easier question that you can determine. All right, so same instructions. So we're going to do a few of these, and then again, I'm going to show you how we're going to use the rules to actually solve problems. So what about the log base 3 of 3x plus 7 minus the log base 3 of x? So what rule would I use in this one, and how do you know? Yeah, so this would be the quotient rule, right? Because we are subtracting. So this would just look like the log base 3 of first thing divided by second thing. By the way, you can't cancel x's out there, so don't try to do that. You don't have an x in this term of 7 here, so you can't do any simplifications. That's as far as you can go with that. All right, so notice we're doing a lot of different examples today. So different from some of the things we covered in Unit 2 that would take like 15 minutes for one problem. These are like seconds long problems. So you're going to understandably have a few more on your homework, like a few more questions. But just know that none of them are really supposed to take you that much time. So same instructions. In other words, I want you to combine it to a single logarithm if you can. So the first thing we're going to do is handle these numbers in front. Where can we move these numbers in front since we're going backwards the other way this time? Move it to the exponent, right? So this will be the natural log of x to the 4th minus the natural log of y to the 7th minus the natural log of z cubed. Notice that like every number stays with its own little part, right? You never send a number to another piece. So this rule was because of the power rule, or this step was because of the power rule. But then how would we combine this to a single log? So I'm going to start you off here. So it'll be the ln of what? How do you decide what goes where? The positive things go where in the fraction? Anything that's positive like this one goes on top. What about the things that are negative? Where will they go? On the bottom. So that's it. Okay. Positive things go on top because that's where positive exponents belong. And negative exponents go on bottom because that's where negative exponents belong. So what we're going to transition to moving forward is being able to use these rules to our advantage to solve equations. But we're not really quite there yet. But I want to give you kind of some background of where we're heading in the next lesson or so. So don't pay any attention to the fact that we have x's. Okay, right now I'm just asking you to identify what rule needs to be used, right? And you decide that because of the plus sign. So what rule needs to be used then? Product rule? So what does product rule say, basically? It says that we can combine them to a single log by doing what with the two things? Multiplying them. So it's going to be x plus 1 times x minus 3. And then I'm going to put a bracket around this because it's log base 2 of the whole thing. But then I think we can clean this up a little bit by foiling it. Okay, so the log base 2 stays. Then if you FOIL it, you're going to get x squared minus 3x plus 1x, so that would be minus 2x. And then 1 times negative 3 is negative 3. So some of this kind of stuff is what we're going to head to next time. Okay. What if it would have been a minus instead of a plus? How would this problem have changed? We're not going to do one, but how would it have been different? Instead of this times this, it would have been what? This over this, right? So it would have been very, very close. Okay. So before we transition to what we're going to talk about next time, there's a couple more things I want you to know about logs. So notice I put 2 stars by this. I don't do that very much, so that must mean I really want you to know this. There is something with logarithms called the change of base formula. What do you guess that it does? It allows you to change the base. Okay. And here's the formula, and then we're going to talk about why you would want to use it. If you have the log base b of something, okay, the log base b of a, you are allowed to change it to the log of a over the log of b, and you're allowed to use any base you want. Okay, so what bases do you think we're going to probably prefer because we'll be allowed to use our calculator for them? What are the 2 bases that we can use our calculator for? Base 10, right? And what else? Base e, which we call that what else? What's the base e thing really called? ln or natural log. Okay, so let's look at a problem where maybe a change of base would be helpful. What if I asked you to evaluate What if I asked you to evaluate the log base 5 of 40? So I want to talk about why this is actually a challenge for us to do in our head. Why is this going to be a challenge? Well, what question is this really asking? What does this mean? What do I need to raise 5 to the power of to give me 40? So what do you notice is the problem here? I mean, it's not that there's nothing, but it's certainly not a whole number, right? 5 squared is 25, and then 5 cubed is 125, right? So like there's nothing that covers 40, okay? So we're going to use the change of base, and the change of base formula just says that you're allowed to do log of the big number over log of the base, okay? And why is that helpful for us to be able to do? We took it out of base 5, which we don't really have a calculator that can help us, right? And now we put it into base what? This is really base 10. Okay, so we're going to use our calculator to help us out there. So it's going to be the log of 40 divided by the log of 5. Not surprisingly, we're not going to get a pleasant answer here. We already talked about that the answer wasn't something we could come up with on our own, right? So the answer comes out to be approximately 2.292. Just so you know, we also could have used ln if we wanted, okay? Because remember, this works with any base. So you could have also said the natural log of 40 over the natural log of 5. And just so you know, you'd get the exact same answer. So the change of base formula is helpful because it changes it from a base that is not so good, which is 5, right? We don't have a calculator for that. And it lets us change it into something we have a calculator button for, okay? You don't have to, but you can check your work here. And I think it's good for the understanding purposes. So, in other words, if you raise 5 to the 2.292 power, what should you get awfully close to? 40? Okay, so let's see if that works. So we're going to raise 5 to the 2.292 power. And notice we don't get exactly 40, but how close is it? It's pretty close, right? So it's going to be about 40. By the way, we're going to look at one more, but you also could have kind of already known that it was going to be 2 point something, okay? And let's talk about why. 5 squared would have been 25, right? So that was too small. And then 5 cubed was too big, so that tells us it's between 2 and 30. Okay, so you kind of can guesstimate the answers if you want to, just kind of optional. So what about something weird, because my math lab tends to come up with some weird stuff for change of base. Of course, pi is 3.14, blah, 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 okay, but all the calculators have a pi button on them, so it won't really matter. So we definitely can't figure this out in our head. Why? What's this asking us? Pi raised to the what gives me 400, and like, I don't know, right? Like, that's weird. 3.14, blah, blah, blah is super weird to even think about. Okay, so I don't like it being base pi, so I'm going to change it to be another base. I can either use log or I can use ln, okay? But it's always log or ln of this one over log or ln of that one, right? So think about like base equals bottom. The base number always goes on bottom. So this would be natural log of 400 over natural log of pi, okay? Or it could be log of 400 over log of pi. Doesn't really matter. Okay. So the pi button, if you have a TI calculator, is here. So it's actually above the little exponent button. So I would use that rather than 3.14 because it'll be more accurate. But if you punch this in, you're going to get 5.233. So how could you check your answer if you wanted to? This is an optional step, but how could you check it to make sure you were right? Pi to the 5.233 power better be pretty close to 400. Okay, so you can kind of check to make sure you're correct, but it's not necessarily required. Okay, so I want to look really, really briefly at the graphs of logarithmic functions. Just like logs, the equation form, we don't really prefer them. We probably don't prefer log graphs either. We probably would more prefer exponents. So I want to look at the graph of 10 to the x versus the graph of g to the x equals log of x. Why do you think I want to look at these side by side? Because what's the understood base for log log? 10, right? So these are inverse operations of each other, okay? So I'm going to make this kind of quickly here. If you wanted to, you could come up with an XY chart. Okay, we did this before when we looked at exponential graphs. So notice I'm going to pick my go-to powers, but I'm going to get some pretty steep numbers here. So remember what we talked about when we graphed like 2 to the x powers, I think the one that we graphed in class. So this one's just going to be just like that, but just steeper. So it's going to be 0, 1 here, but then the next point's going to be at like 110. So I'm just going to kind of fudge it here because I just kind of want the general shape of the graph. So do y'all remember that exponential graphs have this look to them? They go up really sharply and then they approach the x-axis. Okay, so what would we do to find the graph of the log of x, though? Now, admittedly, are we comfortable with logs at least as much as we are with 10 to whatever power? Not so much, right? But the biggest thing that you can do to help yourself is just swap x and y because they are inverses. And that's what we do with inverses. So you can come up with the table using its counterpart over here. Okay, and all you're going to do is swap the locations of the table. So this is going to be -2 to 2. And these values are going to be the same, just switched. So when you go to look at what the graph looks like, it's going to go through 1, 0 instead of 0, 1. And then it's going to have the point 10, comma 1. So if this is 10, it's going to do this. So essentially, the graph looks really close, but what does it look like it did compared to the blue guy? It looks like it's like sideways, right? And that's exactly what it is. It's literally the sideways version. So instead of going up forever, it actually goes to the right forever. Okay, so we won't do another one, but what if I asked you to graph 4 to the x power and log base 4 of x? How would 4 to the x look different than 10 to the x? It would be the same shape, but less steep, right? And then 4 to the x would go sideways, or sorry, log base 4 of x would go sideways. So the last problem of the day is I want you to be able to describe the following graphs. And I don't really mind going quickly through these because I really feel like you should be able to do these based on what we've already covered multiple times this semester. So if I ask you to describe for me the graph of the log of x plus 4, okay, note that it would look like the red graph. Mine's red. You can write whatever color you have. Okay, so it looks like the red graph, but what? But shifted up 4. So what about this? What about g of x equals the log of x minus 3. So notice, rather than the minus 3 being at the end, where is it? It's inside. Okay. So what is this graph going to look like? It's going to look like the red one again, but shifted how? Shift right 3. Remember, it goes opposite. So what about this guy? What about f of x equals negative log of x? Okay, it's going to again look just like what? It's going to look like the red graph, but what change? Reflect over something, right? Which one is it? Yeah, it is the x. Okay, reflect over the x-axis. Okay, so I'm just going to say etc. here, because how many changes are there total? Do y'all remember? 6 total transformations. And we don't necessarily have time for them all. Okay, but I think you kind of see the point, right? And if you need to, you can go back in section 2.5 and look at these. So remember, there's also reflection over y-axis. There's also vertical and horizontal stretches and shrinks. Okay, so you should be able to do